Wow, you made it. This is the last session of the RIC, and you chose us, so thank you. By this time, Thursday, coffee is wearing off. This really is the last of the last. And so for folks who are online following, it is a packed room, standing room only. Even the front row seats are filled-ish. I'm using some liberties on this. But I do want to thank you for coming out and for being here in person especially. Again, the last session of the RIC, it's usually after a week of a lot of handshaking. If you're an introvert like me, you're at zero, right? So thank you for coming. If I'm honest though, this session kind of sells itself. It's space nuclear. I mean, it's like peanut butter and jelly. You can't find two cooler terms and put them together. So you're in for a treat. You chose the right one to come to for all the RIC. You could have gone and seen the chairman speak. You could have gone and seen commissioners speak. But this is going to be the treat. This is going to be the highlight of the RIC for at least for me, because I'm super excited for the speakers that we have. We're going to have a bit of a competition. You guys don't know this, by the way. We're going to have a competition, and it's going to be a modesty competition. Because as I'm reading through the resumes of our speakers, I'm like, holy smokes, these are brilliant, brilliant people. And yet, when they come up, I'm sure they're going to be incredibly modest, because you hear them speak, and there's like, oh my gosh, there's this genius behind these people, but they're real people. And Lindsay, there's a lot of information about you on the internet. There's a lot of stuff out there. So I'm not going to read Lindsay's bio. You can find it online. But if you Google Lindsay, a lot of cool stuff. And we're almost like brother sister. I don't know if you know that we have a lot of intersecting areas. So Lindsay studied electrical engineering. That's my major. You also are a pilot, and I took some pilot lessons, never quite finished, right? And I read, or I think either said or read something which is kind of cool, which I liked a lot, and is that you were inspired by Apollo 13 when you were in high school, so it means we're about the same age. And I remember, a small story is I snuck into the theater when I was in my senior year of high school to go see Apollo 13 because it was sold out. So it's not like I was just being cheap, but it was sold out. So I sat on the floor to watch Apollo 13 and sat kind of mouth agape as an engineer, aspiring engineer, watching this movie, totally inspired by this movie, and actually worked for NASA for a couple of summers kind of based upon this inspiration I have. I ended up at the NRC eventually, and no regrets there, but really have a lot of love for what NASA does. Now, speaking of modesty, I'm a pretty good engineer, and I'm really good at what I do, but I am not a good father. And I'll tell you another story. 2 weeks ago, my son, who's almost 13, movie night, I said, son, it's time for you to see Apollo 13. We watched it, 2.5 hours of the movie, and the kid says to me after the movie, Dad, it was okay. I didn't really like it. I thought, that's it. I've given up. So he's not here today because he's not into space, apparently. But that was unfortunate. So, oh well. So, we have a clicker. Step through a couple slides, a couple of housekeeping items. Obviously, you're here for one giant leap for humankind, using nuclear power to explore space. Nuclear space, gotta beat it. We have Lindsay, Joe, Tina, and Kevin, and I'll introduce each of them as they come up. But our first speaker is Lindsay. And before we jump into that, a couple more housekeeping items. If you have any questions for folks, or you just want to follow up, I did want to put up the contact information for Tina and Stephen Shockley, who were the coordinators for this session. Tina, thank you so much for putting this together, and Stephen, who's on training this week. But if you have any questions, we're a small agency. We answer emails like quickly. So if you have any questions, you got Tina's email, you got Stephen's email, you can get my cell phone or email address. Happy to answer questions if you have anything afterwards. And then most importantly, bust out your cell phones, not to do emails, not to chat with your buddies, but to take the QR code down. If you have questions today, this is your best way to get questions in. And with that, I'm going to hand it over to Lindsay Calvin. So Lindsay, again, a short introduction. Lindsay is the Fission Surface Power Project Manager at NASA's Glenn Research Center in Cleveland. Again, I had the pleasure of working there. Actually, it was LRCIP. It was the Lewis Center while I was working there, and it changed names to Glenn. This is several years back. Before that, she served as a technical lead and the Deputy Program Manager at the Navy's Electromagnetic Pulse Office at the Naval Surface Warfare Center in Dahlgren, Virginia. Over 10 years of experience with DoD. She worked on the U-2 and Global Hawk aircraft, which is very cool. In addition to her electrical engineering degree from Evansville, she also has a professional certificate in system engineering from the Naval Postgraduate School and a master's degree in nuclear engineering from Penn State. So where I called you my sister, you kind of like took my starting point and then ran with it, which is awesome, So again, please welcome Lindsay, put your hands together and give her a warm applause and welcome her to the stage as she talks to you about Vision Service Project. Thank you.
There you go. Testing. Great. Thanks, Victor, so much for that kind introduction. We'll go ahead and get right into it. Okay, to set the stage a little bit for why we are looking at nuclear power in space, you can really look at what NASA's focus is right now is to go back to the moon and eventually get to Mars. And we're going to use the moon as kind of a learning or a test bed for the Mars activities down the road. But this is all going to be enabled through the Artemis missions. And out of curiosity, how many have heard about Artemis? Oh, good. Yeah, you'd be surprised how many times I go out to the public and maybe half, if any, have heard of Artemis. So this is a really great time for the country where we're going to go back to the moon for the first time in over 50 years since Apollo. Those are enabled through Artemis. We have numbered Artemis missions. Artemis 1 has already happened. That's where they tested the Orion space capsule that will have the astronauts in it. Artemis 2 is, I believe, slated for next year now, but that will be where they take a set of astronauts up to lunar orbit, and they don't actually get to step foot on the moon yet, but they'll get to go around the moon. I think that would be really hard for an astronaut to get so close and not to be able to get off of it, but it's not until Artemis 3, and so keep your eye out for that. But Artemis 3 is going to be the one where we do step foot back on the moon since Apollo, so it's really going to be historic, and I believe that was slated for 2027. But it's all to go back to the moon first, but you need a source of power, and that is a focus and a priority right now for the lunar architecture team. Is what does that source of power look like? And at first you probably won't have a whole lot that you're going to be powering up. And so maybe solar can get you by or batteries, but to be able to have a source of power that's very reliable is being kind of focused in on right now. And so nuclear power in space on the surface of the moon is probably going to be augmented with other things, but eventually it's really going to pick up a lot of the load if you ever want to do they call it in situ resource utilization, or ISRU. So that's mining things out of the moon dirt called regolith, and then extracting water that's in the form of ice. But nuclear, and actually I'm getting a little ahead of myself. I'm just going to go to the next slide. Nuclear, it allows you to kind of do that. So if you look at this roadmap of the moon, the left-hand side is, we call it our first generation fission surface power system, or our first generation reactor. And the power out that we're looking at, we've kind of targeted anywhere from maybe 10 kilowatts electric up to about 40 kilowatts electric. And I think in the end, what we're going to settle on is whatever can fit on a lander. So we are going to be limited by mass getting this up into space. So that's really going to be where, in the end, when we get this request out to industry for proposals and the build of the system, that power out is really linked to that mass limit. But let's say theoretically that we have a 40 kilowatt system, 40 kilowatt electric, and that's enough to help get power an early Artemis habitat or rovers. But down the road, we want to help kind of get that lunar economy going and really support industry in those efforts. And so you're probably going to need a little bit more than 40 kilowatts electric to do that, especially if they start looking at microgrids and really getting some of that heavy power draw going. And so maybe a future generation, or think of it as like a block upgrade. If any of you are familiar with DoD and aircraft, they always kind of block upgrade their aircraft to meet needs. And so maybe a block upgrade to this first generation system is a bigger system. Maybe we can get a few hundred kilowatts of power out, or maybe even up to a megawatt down the road to be able to support the the electricity needed for those mining activities, maybe even 3D printing your own parts on the moon instead of waiting for a shipment from Earth to come in. And then another future generation from this first one that we're working on today is over on the Mars. You see, maybe these are smaller because the Martian atmosphere and environment's a little bit different. Maybe we can't necessarily get a megawatt system up there. So maybe those are smaller, and you can link these reactors together like Christmas lights. If you need 50 kilowatts of power and you got 5 10 kilowatt systems, you could link them together. And so that's going to be another block upgrade, so to speak, from this first generation that we're working on today. And we want to certainly eliminate the amount of redesign down the road. And so we're working closely with the Martian architecture team or the Mars architecture team to understand what those environments are and try to build those hooks in, those interfaces into this first unit as much as we can so that we're not having to do a drastic redesign down the road. And then for the agency, the technologies that we're investing in for fission surface power, and I'll go down into those in a slide here, they are all, I'd say all, most of them with the exception of an electric thruster are going to be directly beneficial to nuclear electric propulsion systems. So those spacecraft, the ones that you see in Star Trek or Star Wars, and they got this brilliant blue glow coming out the back of them, those systems, those thrusters are actually being tested today. My first day on the job a couple years ago at NASA, and there was one of them in one of our big vacuum chambers at Glenn Research Center, and it felt like I was working in a science fiction movie, but it's here. It's not something down 20, 30 years down the road. Like this stuff is being tested today. And so we want to make sure that we're able to leverage the investments making on this this nuclear reactor, that they are useful for nuclear electric propulsion plans down the road. And then the last thing I want to point out on this slide, the lower left-hand corner, we are very much interested in the movement towards these small modular reactors and microreactors in the nuclear industry today. Kind of seeing where the companies are taking them, because every advancement that's made on the terrestrial side is useful for us, especially with public support. That is a challenge. Back in the day, there was a lot of protests for radioisotope power going into space, and so far I think the public support is more positive than it has been in the past. I've been to many events with the public, and I've never received a negative comment or any kind of protest or anything like that. I think people are just excited about the prospect of nuclear power up there in space, and then what it can bring to those here on Earth in these more remote locations and possibly disaster areas, what small modular reactors can do. And so we're excited whenever we see things coming up on SMRs, and we're just kind of cheering it on the side. And I think we're also seeing interest from industry with what we're doing on fission surface power, because we're investing in components and parts that are going to have to be really reliable for this reactor in space. We're going to build this to have a design life of 10 years without the need for refueling, without the need for maintenance really either, because it may be some time before we have astronauts up there to be able to do that. And so in the terrestrial nuclear world, you may be able to go replace a part every few years in a reactor here, but we're not going to have that luxury in space. And so we are really going after kind of pushing the bounds of the life and the reliability of some of these parts. And so I think that's useful for industry. In the end, the parts may end up costing a little bit more money, but if you can get 10 years of life out of them instead of a few years, that's going to be useful. And so we're seeing a lot of interest from the terrestrial side with our project as well. Okay, keep going here. One decision that came out in December, and this was really key for our project, is this decision from the Mars architecture team. This was really kind of our first locked-in customer. And fission systems are not something new that NASA has invested in. They've been investing in fission systems, the technologies, for about the past 20, 30 years or so. Back in early 2000s, we were planning to go study Jupiter's icy moons for 20 years. And we had a nuclear electric propulsion system to do that. It was about 200 kilowatts electric. It got through a lot of the design. However, it became very, very costly. And so that project unfortunately got killed. It was called Prometheus, or JIMO, Jupiter Icy Moon Orbiter. The agency said, go back to the drawing board and come up with an affordable first fission system for space. And that was about 2010 or so. And we were targeting a 40 kilowatt electric system back then. However, it was done during the Constellation period for NASA, which again took a lot of hits for the agency, and that unfortunately got rolled up into it. We did have a little bit of money though. About 2015 to 2018, we worked on something called Krusty, or Kilopower, and that was a 1 kilowatt electric reactor. And that got through a successful test out in Nevada in 2018, and it was really significant because that was the first time since the SNAP-10 program from 1965 where we have successfully tested a nuclear-fueled fission reactor in the space environment. It did not fly. Krusty didn't fly in space, but it was tested in a relevant environment. SNAP-10 did fly in space, and that was the only one that we've been able to successfully launch in the country, and that flew for 43 days, and the thing that brought it down was not the reactor, it was an electronics issue. And so we've been trying to get these systems up there ever since, and it seems to usually be budget that kind of gets them, we get going and then the budget kills them. But this time we've got this really firm lock-in customer, and I believe Artemis is going to be around for, it's kind of one of those things that feels like it's going to stay. And so we were really excited when this decision came out. The Mars architecture team said, this was the first architecture choice, even above what the rocket is to get them to Mars. This was the first one they said is they need a primary source of power, and we have decided it's going to be nuclear fission. That was really, really exciting. And if you want to learn more, you can Google Mars Architecture Decision, or ACR 2024, and find that document that lists that decision. A couple years ago, we awarded some design contracts to industry to help us understand what this first-generation reactor could look like and what the cost of it would be and the schedule to be able to get it built and delivered to NASA. And so 3 partnerships were selected. They award these design contracts. You had Lockheed Martin with BWXT, Intuitive Machines with X-Energy, and Westinghouse with Aerojet Rocketdyne, who is now L3Harris. And we didn't levy a whole lot of requirements to the companies. A lot of it was design goals, but the 3 requirements we did say were 40 kilowatts electric for 10 years, that this could withstand launch and vibration loads, and then the third one was safety related. We wanted to make sure that a radiation dose received by an astronaut wouldn't exceed 5 rem per year at a kilometer away from the reactor. And so the companies took that. Everything else, like the mass, we had a 6 metric ton mass limit for the reactor, and that was everything. That wasn't just the reactor and the core and the shield, it was the balance of plant. So it was your power conversion system too, along with the cabling to get that power a kilometer away over to the user interface, the 6,000 kilograms. So that was a goal, and then as well as a volume, what you could fit within a lander or a rocket to get you there. And this is just an image of what the results of those designs looked like, and you can see they all look a little bit different, and that's an artifact of not levying too many requirements on the contractor. They were able to really kind of think outside the box and come up with really unique concepts. We learned a lot from that. They were able to identify challenges that we might have moving forward with setting the requirements for the flight system. And so we on the NASA side, we're working closely with Department of Energy to come up with a good set of requirements moving forward for what the flight unit, we would like that to be built to. And we're kind of currently in that process of getting through some milestones and being able to draft up that request for proposals that will go back out to all of industry to bid on. And the intent is not for the government to build this reactor, but for industry too. And so the chances are wide open for any company to come in But we really learned a lot from what we call that our phase one effort. And then while industry was working on their designs, we also worked on one on the government side called our government reference design, and that's what you see on the right. And we took all the requirements we levied on the contractors, and we kind of came up with our own concept with the Department of Energy, served a couple of uses. One was to make sure the requirements made sense, that we didn't give industry something that couldn't be achievable. And then also to serve as kind of a sanity check. As we were sitting in on their design reviews, we were able to kind of bounce that off of what we found on the government side. But you can see that conceptual image there on the right. One thing that we are likely to change, for example, is that mass target. I can say that it was difficult to meet for any of these designs, and we learned from that. And that's an example of one thing that going forward, we will likely adjust that mass target and probably be a requirement instead of a goal. Okay, so just a couple of things now shifting more towards the regulations and policy side. I'm going to talk a little bit about safety. Of the three requirements we put out there, that was one of the three. We recognize the importance of safety, especially when you're dealing with nuclear materials. And it's not just once this is up on the moon or Mars. Of course, it's going to be in kind of a dormant state until you get up there on the surface of the moon, and then we will use control drums, kind of similar to control rods in terrestrial reactors. The control drums will rotate. We'll have a little neutron source there, and that's what will get the reactor up and running. But will be relatively benign until it gets on the surface of the moon or Mars. However, there's work that's got to be done. That integration of the fuel here on Earth as we prepare to have it launched, and just working with nuclear materials. So we're making sure that we're following appropriate guidelines and standards, and NASA does have a number of standards already in place for this. And then once it is turned on the surface of the moon, there are crew radiation limits that are imposed. But we're making sure that we are adequately incorporating all these requirements and standards into that statement of work for the company that ends up getting the contract, that they need to be sure they're following to make it safe. Another couple things I want to quickly mention, NEPA, so the Environmental Policy Act, we are required to follow that. And so we are working even today with some of the NEPA personnel. This is something that Department of Energy will help provide inputs to, but that's about 2 years prior to launch. Let's say we're hoping to get this up maybe 2030s, and so we're still a little bit before that, but we are trying to understand the timing and the costs of all that. And this is going to be a lot of, what does that look like here on Earth, the integration of the fuel, just the environments and having that nuclear material in place. But NEPA is one, and then the other is NLAP, Nuclear Launch Authorization Plan. We do, this one is required to begin quite a few years before launch, estimating about 7 years ahead of launch. And there are a number of things that have to happen before you can launch nuclear material, and they are listed here. One thing I want to point out in particular is this INSRB, INSRB. NASA does have a key part in that. We have a nuclear flight safety officer who's actually here in the audience, and he is the secretariat for the INSRB, but that is Interagency Nuclear Safety Review Board, and then also FAA is involved, believe it or not, too, which actually you guys probably do already know that. But these are all, we want to make sure that what we're doing is safe in the end. And I will repeat safety many, many times, and I try to drill that into the team as well. In the end, we want to make sure that this is safe and we don't have any incidences. But that INSRB is, we will meet an INSRB and they will look at the safety aspect and what are our contingency plans and everything. We want to make sure that we're doing everything according to policy and regulation in the right way. I was recently briefing a group out of the FAA, and I decided to keep this slide in there because it is one of many agencies that we there are regulations for that we need to make sure that we are adhering to. FAA is one of them. They now have this advisory circular launch and reentry of space nuclear systems. And so that is, we have a system that is right down that alley, but that is another case in point. Many agencies involved here. In 2021, there was this Space Reactor Standards Working Group that was convened, and it was kind of led by the NASA chief engineer at the time, but they pulled in 7 federal agencies. And by the way, I believe these agencies are part of the NSERB as well. It's a 7 multi-agency group. But the reps from these agencies, and NRC is listed in here as well, was to essentially assess the current state at the time of standards for the launch of nuclear systems, in particular for fission reactors, and kind of chart that path forward if there are any gaps identified. And so there was a report that came out of that, shown there, and I'll talk a little bit more here. That working group reviewed existing standards, like I said, and there was well over a couple dozen or so standards that already exist. And this is just a snapshot of what some of those were. And so they included standards from NASA, DOE, FAA, ANSI, ANSI, ANS, et cetera. 3 of those I looked through, they were related to NRC, and some of you may be familiar with these standards already. They're shown there, a lot of them dealing with like non-light water reactors, accident analysis methods. But what I wanted to really point out was this working group went and they canvassed the existing array of regulations. There were a lot of them. In the end, they identified their 3 gap areas. One was safe operating practices for fission reactors in space, testing requirements, including facilities, and safety and risk analysis methods. So these are pretty key things that were identified in the end, even though all this stuff, and a lot of those are tied to terrestrial. So that is why you find these gaps, is space nuclear is really kind of that new uncharted territory. But there was we called our technical discipline team at NASA that then identified champions to go and address these gaps. And ASTM is working on a safe in-space operation of space reactors, and I believe Joe's going to talk a little bit about that. They are pulling in industry inputs as they develop that standard. ANS is working on the test requirements standard, and then DOE and NASA are working on addressing the safety and risk methods. Okay, so in conclusion, we are working with a number of stakeholders, and I would say to include NRC. We primarily deal with Department of Energy on this because this is a federal project. However, because we are really going to be using commercial industry to build the reactors, NRC is going to be involved. But we are working with a number of organizations, and there are a number of regulations out there, but there are gaps identified for the safe operation of space reactors, and those are actively being worked on today, which you'll hear from my co-panelists more about. But in the end, our goal is to provide a safe, reliable reactor to the end user, in this case, an astronaut. So with that, I turn it back over to Victor.
Awesome. Excellent.
Thank you.
Give this to you. Thank you, Lindsay. And so please join me in giving Lindsay a round of applause. Really appreciate the presentation. Thank you. And this is a good reminder to use the QR code to ask Lindsay questions. I already saw a bunch of good questions coming in, so please keep those coming. That'll make for some good conversation after the panel. All right, our next speaker is Joe Halakna. And so I described Lindsay as my sister, and Joe, I think we may have some brother connections going on. And we just met right before this panel, actually. We didn't even have a pre-call. But kind of cool, a lot of the ways that our worlds intersected, and found out that Joe worked on the AP1000 for more than a decade, which I did too. But, you know, almost like in a brotherly way, there has to be a little bit of conflict, right? And so I'm a regulator. Joe works for Westinghouse. It's, the designer. And if you don't know the NRC, the biggest compliment we can pay you in inspection space, the biggest compliment is no findings of significance. That's it. I mean, we can't say, I love your plant, they did a great job on the design, it's impressive as an engineer, I'm tickled, none of that. Just no findings of significance. So come to find out you're working on eVinci, which is possibly one of the leading technologies to be used in space, which, again, the engineer in me is thinking, that's kind of cool, but I can't say that, so I can't say it. So regarding the eVinci, no findings of significance. It's really good. So Joe has a Bachelor of Science in Mechanical Engineering from Penn State, also a Master of Science in Mechanical Engineering and an MBA from the University of Pittsburgh. So pretty awesome resume. And again, as a brotherly way, I found out he's a Pittsburgh Penguins fan. Mm-hmm. I'm from DC. I was born in Washington, DC, so I bleed Washington Capitals red. So I guess, give a round of applause to a Pittsburgh Penguins fan, Joe Houghton.
Thank you, Victor.
You can stay there if you like.
Yeah. All right, ready? Yeah, it's great to be here, an honor to be here. Again, it's a very exciting time for space nuclear. Lindsay did a great job sort of teeing this up for me. Obviously, the U.S. has a pretty extensive legacy in this area. While it's maybe been dormant and for the recent decades, if you go back long enough, Westinghouse was proud to be part of the NERVA program, shown here. You can see the SNAP-10A that is on the left-hand side, that Lindsay mentioned as really the only reactor that this country has put into space. And it's been an honor at part of Westinghouse when we were part of those programs. My mentors worked on those, did a lot of the testing out in Nevada on those programs. And even on eVinci, we've gone back and pulled some of those documents out of the library, some of the testing, to look at how do those systems operate, what was the test data, and how can we use that to benchmark not only our eVinci designs, but how can we relate that to the space environment as well. As Lindsay showed, Westinghouse has been an active participant in achieving some of looking at how can we apply the technology that we've been developing, how can we design some of these systems to achieve the missions, and really, again, move us into this next generation. I mean, the rapid growth of really just the space industry, looking for more power in space, really has brought nuclear fission, as you can tell by the Mars architecture type decisions, that hey, there's a prominent place for nuclear energy here to deliver that resilient, reliable power source, high power source. We're talking in this case, right, kilowatts up to megawatt. Where again, we've launched radioisotope type systems. They've been very effective, but again, very, very small power levels you're talking there. So as we transition, over the next decade, we see great opportunity here with the technology that we've been developing, especially on the eVinci microreactor program. That has been a project that's grown out of a partnership with Los Alamos National Lab in particular. The heat pipe technology that they've developed and applied to some of the designs, such as Kilopower and Krusty, looking at how you can take that technology, that passive heat transfer technology, and apply it into reactors. The advantage too for us that we see obviously is a great opportunity to synergize and leverage what terrestrial work we're doing and the opportunities we see there to deliver nuclear energy in these microreactor. In this case, we're talking 5 megawatt electric is our eVinci microreactor baseline design. But how can we scale that technology back down to where it was originally envisioned by some of the folks at Los Alamos looking at these space nuclear applications? But to reach that point, as Lindsay noted, I'll expand upon some of those gaps that were identified in some of those interagency working groups, and what is industry doing, and what can we do to help set a precedent and set guidelines for not only the developers of these technologies like ourselves, but also those interagency working groups, those end users, those customers that are looking to achieve these missions and operate these missions, for what is reasonable, what is cost effective, and how can we set clear expectations for what needs to be done leading up to launch of a payload. So again, Lindsay mentioned this. The key thing coming out of this, and there's a couple papers, a special note to Lee Mason, who championed some of these standards being developed. Also presented some of this work as well back at the ANS NETS conference back in 2022. But again, identified, I'll say, the key 11 sort of agency findings, recommendations. So you can see some of the lower, let's say, lower priority, lower rankings on the screen there. Things around storage, transportation, things that have probably more synergy to our domestic or terrestrial projects. But obviously leading through dose analysis and even decommissioning of what we're going to do at the end of life of these systems. But the high priority targets there, again, testing. Obviously, going back to those historical programs, a lot of testing was done. But how do we do that in an effective and safe and in accordance with today's environmental policies? Risk and safety analysis, lots of folks involved there. And then again, how are we actually going to operate these reactors? There's a lot of different missions, a lot of different places that folks want to go, whether that's the moon, Mars, different challenges. You can look at many of the lunar landings that are being attempted now, are all going to different locations. I'll say the lunar South Pole, where is one target where there may be water, has particular challenges for its location in terms of communications. So how are we actually going to operate these systems? And what guidance can we do and what testing do we need to do to demonstrate that we can do that safely and effectively? So the high priority ones I'll capture here. So what are we doing in terms of testing requirements? So why is that? So if you look at the challenges, how do you get space nuclear, as Victor sort of alluded to, some great buzzwords, gets people excited, but those are two very challenging environments in and of itself. And then you've got to mix them and push them together to achieve both a nuclear relevant environment and a space relevant environment. And that's very difficult to do here on Earth. So looking at both what testing needs to be done, should be done, how can we leverage ground testing, terrestrial testing environments, but what do we need to do also from a facility perspective? What facilities do we need? What's the quality assurance into those facilities? And how do we demonstrate that, again, following obviously those tests will be done on Earth in accordance with DOE, NRC, and other within the regulations of those facilities. But again, starting to drive towards standardization. Again, as we looked at early phases of FSP type programs, a lot of discussions are, how do we get to launch? What testing do we need to do? And there are many different opinions, depending on what may be the mission requirements. So how do you try to provide a framework that is both flexible, inclusive, but also provides some clear expectation for how can we actually get to and avoid those budget issues of past projects, not just space projects, but nuclear projects as well, where you can set a very clear standard going forward for what to expect and for what to plan to. Safety and risk analysis methods, so obviously a lot in there. There's guidance in NSPM 20. There's also, again, probabilistic risk assessments, risk-informed methods that are being developed for terrestrial mech reactors. As part of the Vinci program, we've been piloting some of the risk-informed, performance-based approaches in conjunction with the NRC and the DOE, and leading on how can we use that to inform throughout the design process leading up to the qualification and licensing of a system. So I'll point to and then the last one there, again, safe operating practices. What are the operating principles for these types of systems? And starting to get into challenges that we just don't have in the terrestrial space between communication, how are these systems, are they going to truly be autonomous, and how do you really plan to operate these from the ground and or from, let's say, the lunar or Martian surface. So in terms of sort of who's taking up the call, so the ANS working group that I'm leading, 31-1, is working on the testing requirements. There's an ASTM working group, I've got it on the next slide, that's working on the last one. I think there's a lot of folks working on gap number 8, as I think a number of folks in DOE in particular and at NASA. And then even just over the last few weeks, ASME has been interested in the Joint Committee on Nuclear Risk Management and taking a review of what they could do and apply from their other work into filling gap number 8 there. So just some points of contact. So I sort of mentioned that work there. And if you're interested, on the Joint Committee, you can feel free to reach out to myself or Tina afterwards, and we can get you in contact with those folks. You can see some of the names there. The goals of these programs, I won't read the goal statements maybe, but the mission or the takeaway I have at the bottom is really looking for these standards to be technology and application agnostic. How can we provide guidance? The missions are all going to be different, which is a challenge when you look at where you're going. Things like radiation shielding is going to be vastly different no matter what your flight plan is, where your final location is. But how can we provide something that really looks, I will say we are focused on fission. Not to say it excludes fusion, but there are other folks that are looking at fusion. So I would say guidance may be applicable for those types of systems as well. But again, whether you're looking at electric propulsion, thermal propulsion, payload power, or surface power, where our goal really is to make sure that we can provide a standard in these cases that is applicable and flexible enough to include any of those applications. So in terms of 31.1 in particular, so some of the challenges or just requirements that we're looking at, is a couple of different things, right? What ground testing needs to be done? Do you need an actual twin? Can you use a digital twin? Are you performing testing on the flight unit itself? If you go back to NSPM 20, one of the key requirements there is that you are not launching essentially an irradiated or a reactor that has already been used. So that provides some additional risk in the sense that the first time that reactor will go critical is in space. So how do you manage what you're doing pre-flight? If you have sort of a physical twin of that you can do enough testing on. This is where obviously leveraging of terrestrial microreactors of very similar systems can come and play a large part to de-risking and showing there's large similarity from a criticality, reactivity control, and from a physics perspective. Again, what nuclear testing are we doing terrestrially? How can we sort of modularize these systems, qualify systems individually, and then obviously bring them together maybe at the launch pad? And again, there are different requirements. There's going to be different regulations, different requirements. The risks are different for these systems, again, when you look at both launch and operation. And how do we make sure that we're looking at both this in context of space nuclear and the space environment? And then obviously some of the challenges, if you look at the historical programs for propulsion in particular, how are we going to comply with our environmental standards today? There's a figure there of how we might have an NTP facility that is able to operate for longer periods of time, to actually operate a reactor engine without dispersing that gas to the environment and put anything at risk. But at the same time, we're trying really to, in the aerospace phrase of test as you fly, really try to mimic and be as relevant to the environment that you're going to see. And in this case, the two challenging environments we have make that a very challenge for how do you really verify the system pre-flight. And again, what can you do at different scales to try to do that cost effectively? And again, so anticipating those environments is a challenge. There are facilities, whether they're at Glenn Research Center, there's large vacuum chambers NASA has. Obviously, there's a lot of nuclear test facilities in this country. So some great opportunities. I think where a lot of the industry and NASA and DOE and others are all interested is how can we pull those things together in a cost-effective manner to make sure that these missions are a success. So my last slide here, I liked this roadmap from a paper a couple years ago. A little bit of an eye chart, but essentially the swim lanes there are sort of manufacturing demonstrations, non-nuclear tests, nuclear tests, and then really reactor physics and reactivity control type experiments. So as you move left to right, the colors also, I'll say, give you an indication of sort of TRL raising. Not my favorite metric, but again, something that is somewhat standard across the DOE, NASA, and other agencies. But also really looking sort of from separate effects tests really is the focus of as you move left to right towards more larger integral effects tests and larger demonstrations. I think the challenge here is there's a lot of detail, there's a lot of different experiments, tests that need to be done. Again, how can we provide guidance in these standards that are being developed to either simplify or set the clear expectations? So if NASA or others are looking to fund and execute some of these projects, there's inherent agreement on what testing is going to be done, needs to be done, and therefore it can be effectively budgeted so we can meet expectations on making these missions a success. So this was one really good chart I like to use as a framework for how can we sort of start setting the standard, how can we start to bucket a lot of these tests into a program such that we can be successful. So with that, again, contact information. I hope Lindsay and Victor both excited you enough about these missions. If you want to be involved in any of these standards, feel free to reach out to any of the contacts here, Tina or myself or Lindsay. And again, or if you're interested in the ASME committee or any of the other DOE work, we can get you in contact with those folks as well. So with that, thank you very much.
Thank you, Joe. Appreciate the presentation. And again, a reminder, if you have questions for Joe or any of the panelists, now's a good time to pull out your phone and scan the QR code. I realized I didn't do a very good job introducing myself. So before I introduce Tina, I'll introduce myself a little bit. I'm Vic Hall. I'm a acting director in our division of systems analysis in our group that does nuclear regulatory research. So research is the name of the game for what we do. But really, I aspire to be Abraham Flexner. Does anyone know who that is? Anybody? Raise a hand. Abraham Flexner? I had to Google it too. Abraham Flexner was Albert Einstein's boss. And that's what I want to feel like, because there are some really, really smart people at the NRC's research. So on that note, let me tell you a little about Tina Gosh. Tina is, she's one of our senior reactor systems engineers. She also serves on the Interagency Nuclear Safety Review Board, the INSERB, as Lindsay mentioned. And just to give you a little bit, she's never going to tell you this, but just to give you a little context, the previous NRC member of the INSERB was my boss's 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 boss. And when he retired, they said, well, let's just pick the smartest person we got. So Tina took that role over, which is amazing, Tina. I'm always blown away by Tina. Tina has a civil engineering degree and operations research from Princeton, an MS, Master's in Technology and Policy from MIT, and a PhD in nuclear engineering, also from MIT. She's also the recipient of the 2016 Arthur Fleming Award honoring outstanding federal employees, and I happen to know that she has impeccable music taste. So with that, Tina, I'm always learning something new when you speak, and I'm looking forward to your presentation, even though I've already seen the slides. So with that, everyone give a round of applause for Tina.
Thank you. Thank you, Vic. Yes, Vic has great taste in music. I will. I can attest to that. Oh, who has the clicker?
Where'd it go? I took it with me.
Thank you. Okay, so I think Lindsay set the stage nicely for some understanding of why are we even talking about, space fission reactors, and Joe talked about some of the industry consensus standards are in the works. I wanted to focus a little bit about what other kinds of guidance are out there for kind of the whole of missions. So. The exciting part of the missions is usually the part that happens out in space, but before we get there, we have to start here on Earth. And I just want to clarify something up front. NRC has no authority to regulate anything on the moon. So when I talk about our NRC's part of this, it is firmly the Earth terrestrial portion of it, and then everybody else gets to do all the other exciting stuff. And in fact, we don't even regulate our, we're not the authority for launch. We even hand that off to the FAA. So really the NRC's is the most, mundane part of this whole thing, but someone has to talk about it, so that gets to be me. But before I get to, so really the focus of most of this talk is on purely commercial missions, but before I get there, I just want to briefly touch on the Interagency Nuclear Safety Review Board, which Lindsay already mentioned. So the INSERB, I'll just call it for short, came into being in late 2019 when the presidential memorandum NSPM was later named NSPM 20 came out. That's what started the INSERB, and I think we've already named the 7 agencies, but I'll just name it here again. NASA, which includes the Secretariat, and then the Department of Defense, Department of State, Department of Energy, Department of Transportation, Environmental Protection Agency, and NRC all provide members to this standing board. And the primary role of the board is to do a safety evaluation for Tier 2 and Tier 3 government missions, or for commercial launches if the Secretary of Transportation requests it of the INSERB. The Tier 2 and Tier 3 come into play because NSPM 20 also laid out safety guidelines, so it is a risk-informed approach. And depending on the projected risk to members of the public for the mission, you're either going to be a Tier 1, Tier 2, or Tier 3. Tier 1 is the lowest risk. And also depending on the type and quantities of nuclear payload you have on the launch vehicle, you'll land in one of these tiers. So again, the board's role is to evaluate safety for those Tier 2 and Tier 3 government missions, and for commercial launches if the Secretary of Transportation requests. So for commercial, purely commercial ventures where the Secretary of Transportation isn't requesting INSERB to do the review, that's going to fall on FAA to do the safety review and be the launch authority. And I'll touch on that at the end of my talk. But in terms of other guidance that's out there, NSPM 20 was written at a pretty high level. It kind of lays out general principles and so on. And the INSERB thought it would be helpful to provide potential mission owners and the public with some more meat with regard to how we, the board, think things are going to work. So there is an INSERB charter and a playbook, which are available on the Nuclear Flight Safety website of NASA. And by the way, all of the slides from this whole conference are available online, and anything you see hyperlinked, you can click on those links from the slides and get to the references directly. And I also have a list of references at the end because one of my primary objectives with this talk was just to kind of put all of the helpful references in one place, so hopefully that will help out. I also want to point out that in summer 2024, the INSERB, our fearless secretariat, led by our fearless secretariat, who's in the audience today, had a virtual open house which shared a lot of good information. And there is the slide set from that open house is available online, and it kind of lays out the historical kind of, the backdrop of safety reviews leading up to NSPM 20 and INSERB, and, talks a little bit, for example, about a couple of the government missions that are in the works right now. So that's a good reference. But I want to move on to the purely commercial scenario. So one good place to start the discussion is the SECI 24008 paper that NRC published last year, and I believe there have been a couple of RIC sessions, both last year and this year, that have talked about different aspects of the contents in this paper. But it is a good place to get a kind of a snapshot of what would be all the different terrestrial regulatory pieces that would have to be covered for a microreactor that would eventually be deployed for space use. The diagram I have in the upper right is kind of a cut of a larger diagram some of you may have seen. The parts that are relevant for the space deployment are, that you may be you'll be manufacturing the microreactor at a facility, possibly fueling it, and then transporting it. The difference between a terrestrial deployment and space deployment is that instead of then using it somewhere else away from the factory site, it's probably going to a launch site, to be launched for space use. I did want to point out that in that SECI, there is an enclosure, and one of the items in that enclosure, which is item 9, discusses the considerations for commercial space applications. And there it basically says that NRC's plan would be to use our existing regulations and guidance for microreactors the same way, whether it was meant for eventual deployment somewhere else away from the factory site on Earth or for space deployment. So again, it's a very short discussion, but it's worth looking at, and the plan would be to use our existing terrestrial guidance for reactors that would have eventual space use too. So, first, typically you would probably start at a fuel cycle facility, and if you see the discussion under option 2B in that SECI paper, it's again a good overview of the regulations and guidance that would be available and useful to look at for fuel cycle facilities. So the special nuclear material requirements are contained in 10 CFR Part 70. And there's a couple of standard review plans that are useful to look at again for understanding what would be required and what would be reviewed in terms of the safety review for different licenses. So similar to, I think in Lindsay's presentation, she named a couple of regulatory guides, that are available. The standard review plans are kind of like guidance for the staff and also for the applicants to understand what the staff would be looking for when an application came in. So again, those are hyperlinked there, and it's useful to look at the contents of those to get an idea of what the requirements are and what would be reviewed when the applications would come in. Then there's transportation. This was the next part of the diagram I showed earlier. And there's an enclosure item in that SECI paper again that talks about transportation of fueled factory fabricated modules. And it talks about both the packaging and the transportation part. For transportation, the NRC has a role as well as the Department of Transportation. So NRC typically will review the package and certify the package, and then Department of Transportation has its own regulations for the transportation part. So both of those have to be taken into consideration. And here again, there is a standard review plan that referenced NUREG for transportation packages for spent fuel and radioactive material. And I referenced some other 10 CFR parts that may be applicable for transportation as well. So all of this, again, NRC for purely commercial missions would be responsible for the terrestrial parts of safety regulation, leading up to a handoff to the FAA. I think this was already discussed, but FAA is the launch authority. So the commercial launches would be, the safety reviews would be handled by FAA. If the Department of Transportation requested, possibly the INSERB would get involved, but FAA is ultimately the authority. And I believe these were also already referenced earlier, but I just point out that there is a new streamlined launch and reentry rule that was issued in 2020, which is referenced here, 14 CFR Part 450. And this, in 2023, FAA also issued this advisory circular, which is meant to guide applicants through the launch and reentry licensing process when space nuclear systems are present. And I'll just point out the FAA has a role in reviewing both the payloads, so the nuclear payloads, as well as the actual launch itself, and whether it was used for vehicle propulsion or as part of the payload. I think I'm going to skip this slide. Joe already covered all the standards under development, so you can reach out to us if you're curious about that. And I think that's it for my talk. I have my contact information, acronyms. We love acronyms, but sometimes we don't always know what those mean. And I will point out again, I have a list of references on the very last slide, so hopefully it's easy to get further information if you want it. Thank you.
Thank you, Tina. So I want to check with our AV folks to make sure. So our last, okay, we got a thumbs up, excellent. So our last speaker is Kevin Lee. Kevin's going to be joining us virtually from just north up in Canada. And Kevin's actually a lifesaver. We had a last minute cancellation for a speaker, so Kevin stepped in and joined us, which is fantastic. I do have the pleasure of working very closely with Kevin. So Kevin, he leads the Canadian Nuclear Safety Commission's, the CNSC's team that analyzes disruptive, innovative, and emerging technologies called DIET. They have a cool acronym called DIET. And, you know, I'm American, and so we're always number one in everything, no doubt, especially when it comes to competing with our northern brothers and sisters in Canada. But when you see what Kevin and his team is doing with DIET, I got to admit, okay, we're still number one, but it's close, it's close. So Kevin is joining us, and I'll mention, I'm going to give a shout out to one of our guys here, Luis Betancourt, who's one of our superstars at the NRC, was invited recently to join their organizing committee or commission, I forget what the term is, but they're basically getting a chance to help join, and it's really bringing together some great minds for some innovative ways to do business. Kevin with CNSC is also responsible for working on advanced reactor technologies and small modular reactors. Again, looking at innovative ways to do business that the Canadians have come up with. So it is my distinct honor and pleasure to introduce virtually Kevin Lee. Kevin, hopefully you can hear us and see us okay, and we'll give you the floor. So before we do that, I'll give a round of applause for Kevin, and Kevin, the floor will be yours.
Okay, so first for the sound check. Can everyone hear me okay? Can I have a confirmation that you're hearing me okay?
Kevin, I think you're coming in, it looks like loud and clear, is that right? You got thumbs?
Okay, perfect, good.
Perfect,
okay.
Yep.
Glad to hear that. Okay, so yeah, thank you very much for the invitation, and it really came about because of personal connections. I think you know, we all do our jobs as regulators, and I think once you have established sort of those personal connections with people like Luis, Tina, Matt Dennis, you know, Trey Hathaway, that's what makes the job fulfilling. When you can compare notes on different things. Tina and I have touched base on numerous projects over the last few years, and it's always a delight to work with her, and I'm glad to virtually share a stage with her. So what I'm going to do today is, first of all, for those of you that may not know, I'm going to tell you a little bit about the CNSC, what it is and what it does. I'm going to explain what DIET is and what the concept behind the DIET program is. I'm going to explain why the CNSC is looking at space-based nuclear applications. I'm going to shamelessly promote the Canadian Nuclear Society's DIET conference. And finally, I'm going to try my best to stay off the topic of hockey. So with that, next slide, please. Thank you. So the CNSC has over 75 years of nuclear regulatory experience. We are one of the oldest nuclear regulators in the world, and we're very proud of our almost 80 years now of safe regulatory experience. Next slide, please. So our mandate, first off, is to obviously regulate the use of nuclear energy and materials, protecting the health, safety, security, and the environment, aligned with most nuclear regulators. We also are responsible for the implementation of Canada's international commitments, and somewhat uniquely amongst, I would say, regulators in Canada and government departments, we have an obligation put on us by the Crown to disseminate objective scientific, technical, and regulatory information to the public. So we have a very robust public engagement group and program. Next slide, please. What's also somewhat unique about the CNSC is that we regulate all nuclear-related facilities and activities in Canada. So everything from the mining of uranium through to nuclear medicine, radioactive waste management, processing of the fuel, and nuclear power generation. Everything in Canada, if it's nuclear, is regulated by the CNSC. Next slide, please. So now we'll talk a little bit about DIET. and what it is. This is a program that kind of came about 6 years ago. And the way it came about was we had gone through sort of our SMR readiness phase. We looked at our regulatory framework, whether it was ready for SMRs, and by and large, we thought it was. And then someone at senior management asked a really good question, and they said, are we ready for everything that comes with it? And what they meant by that was things like AI, drones and robotics, additive manufacturing, the things that we saw vendors putting into their business plans. So we thought, yes, we need to get up to speed on this, and the group was formed. The industry is really developing quickly. We're looking to gain familiarity with these technologies so that we can enable their introduction without compromising safety or security. And we're also looking to make sure that when we provide independent objective advice to the Commission, that staff are conversant with these technologies. And as well, the Diet Group also looks at how we might implement some of these technologies internally. Now, not a lot of this has to do with space, but I will get to that. Next slide, please. So what is the DIET working group at the CNSC? Well, it resides in the Innovation and Research Hub. So what we do, in essence, and what we've strived to do over the last 6 years, is provide sort of an area, a safe space, where industry, academia, other stakeholders can come in and talk to us about new ideas, new technology they're thinking of deploying, to see, how can this be done? How can this be done safely? And it's a very collaborative way that we go about doing this. To be honest, for the first few years, I think industry was a little leery and, maybe a little not believing that it truly was a safe space that was sort of free from either regulatory or licensing considerations. But over the last number of years, we've actually seen a real uptick. And I would say that relationship building with those in industry so that they come to us as well as academia. One thing I should add is that the US NRC also has a similar function in a similar group. You mentioned Luis and it's his team, as well as the UK ONR. And that a number of years ago, we started what we call the Canuckus Group. So the three regulatory bodies get together once a quarter. We discuss the innovation we're looking at. One of the outputs of that was, some of you may recall, the AI paper, the Trilateral Principle paper on AI, that was published in the September 5th. So what are we at the DIET Group? Well, we're really a triage function. We're not a licensing group. We're not a compliance group. We look at the diet that's out there, the diet that industry is proposing to utilize, and we make a determination as to whether or not this is something we should really be looking at. And you would be surprised at the things we've looked at in the past. We looked at fusion initially. Eventually, we realized that we had reached a level of maturity. We passed it off to our licensing teams. So they're now looking at fusion. So it's sort of the incubator at the CNSC where we establish the TRL of a given technology and then decide what we need to do about it, make recommendations on what should be done, and then eventually pass off the technology to a licensing or a compliance division. We don't really become involved in SMR readiness, although the technologies covered may be used in SMR operations. But what we're finding is that I think we initially started this journey looking at how SMRs might use these technologies, and the realization is that all existing facilities are also going to use DIET. One of the things we found very important, and I'll draw your attention to the diagram on the right. When we initially started this journey, we sort of saw it that, there's the physical and the non-physical. So the kind of the physical technologies, be it additive manufacturing, be it drones, robotics, self-driving vehicles, matched with the code-based or the digital. I hesitate to use the term AI. But what we found very important, and we keep coming back to this in any presentation we do as part of the DIET program at the CNSC, is to make sure that the human is always in there, because ultimately these technologies, these diets are really conceived, designed, built, and for humans. So we always want to remind people that you need to start with the human in the loop. Next slide, please. So why are we looking at nuclear power in space? Well, as I said, the cornerstone of the program is really that engagement with industry, academia, and other regulators. And what occurred a number of years ago was there was a number of entities within Canada that I'll talk about in a moment who sort of independently came to the Diet Group just wanting some conversations around the idea of deploying a very small SMR as part of potentially the Artemis mission. And it came from a number of different areas. And what it did is it allowed us to look at sort of the cutting edge of what people were thinking for deployment terrestrial. And a lot of those things that they were looking, or extraterrestrially, a lot of those things have actual real application in Canada, particularly when you look at microreactors up north, remote mine sites. And they're looking at the things that we were looking at. They're looking at, for instance, higher levels of autonomy, enhanced reliance on AI, remote operations, cybersecurity considerations. These are all things that we're looking at actively as a Diet Working Group. We're looking at how those might be deployed. The other interesting thing is that most of these organizations in Canada that are looking to be part of the Artemis mission are also looking at terrestrial deployment. So they're looking at utilizing these reactor technologies that they're developing or they're looking at in Canada as well. So yes, we won't, as Tina said, be the regulator in space. We have no authority there, but we will potentially be regulating the use of some of these reactors in Canada when they get deployed terrestrial, if they get deployed terrestrially. And there is that I think the ability to utilize space-based reactors terrestrial as well. And many of the companies involved believe that too. Next slide, please. So who are we involved with? I put Artemis at the center because that was really the impetus, was the Artemis mission, the call for the power systems. And these groups kind of all came together. Canadian Space Agency approached us. Canadian Space Mining Corporation approached us. Canadian Nuclear Laboratories approached us. MDA Space. So these groups, McMaster, kind of independently. Now what we're finding is there's a lot of synergies between these, and there's a lot of interconnectivity. So for the CNSC, the fact that we're involved in this and looking at it is really an indication of where we have a terrestrial application. The fact that it's potentially going to be used in space is just, icing on the cake. And with that, I'm going to now shamelessly promote the Canadian Nuclear Society's conference. Next slide, please. So this is the conference. Luis has been asked to be one of the organizers and on the organizing committee for this conference. It's a conference that's held by the Canadian Nuclear Society. We're very involved, the Canadian Nuclear Safety Commission, in helping organize this because it really does bring together sort of the bleeding edge thinkers on generative AI, quantum computing, the heart of Diet, advanced nuclear technologies, on everything from additive manufacturing, you name it. There's a plenary session on it. And this year there will be a plenary and technical sessions on space-based nuclear. So information will be going out on this shortly. And if you go to the Canadian Nuclear Society's website, you'll find out information on it. So I've kind of done a very weaving, roundabout way of talking about why the CNSC is engaged in looking at space applications. And again, much of it has to do with the terrestrial potential deployment, but it also allows us to have discussions with potential operators, potential vendors that are going to be utilizing a lot of the things that down the road might be deployed writ large in the nuclear industry. And with that, I have finished my speaking, and that will be it for me.
Well, thank you, Kevin. I appreciate the presentation. And I do want to offer a quick apology for folks virtually. We lost the feed for a few minutes. Hopefully you're still with us, and apologize for the technical difficulties. And for Kevin in the back, if we can pull up Kevin's video, that'd be good for folks here to see him in the room. So we'll move to questions, and I do want to say thank you to folks who put a question in, some really good ones here. Kevin, I'm going to start, it's really a multi-part panelist questions. So we're going to start, Kevin, if you want to answer first, if we can pull your video up, and then this will be for everyone. And this is kind of one of my favorite questions because it touches research, and I'm, involved in research. So the question is, and this is from Sari. So thank you, Sari, for the question. How can research and development approach or address the unknown unknowns? And the variation I might add to that is touching on R&D, right? What is the value of research, especially, and if you've been here at the RIC all week, you've heard efficiency, efficiency, efficiency. Lindsay, you mentioned safety, I think, most in your presentation, and I love there's got to be a balance between the two to some degree. So love to hear your guys' thoughts, and Kevin, you can kick us off on your thoughts on the value of research and how it's going to feed the unknown unknowns and efficiency.
Well, the whole concept behind research, particularly let's say in the nuclear realm, is to make the unknowns known. Thank you, Hill Runsman, for that. How can I put this? With the uncertainty you have, I think one of the best ways to look at it, and for those of you who have read the paper that we did, the trilateral paper on AI, there's a great little diagram that I think Matt Dennis from the US NRC was really instrumental in putting together. And it looks at the risk around AI. So you're looking to quantify when you really need to start thinking seriously about what's going to happen. And I encourage you to take a look at that diagram because I think in essence, what you're trying to do through that diagram is say that there's a certain level at which, and I'll use the term, the unknown unknowns become such that you're going to have very much safeguards in place. And in terms of how research plays into that, well, obviously the whole idea is to deconstruct those unknowns, make them known, and then therefore have a safer implementation. I don't know if I've answered that very well. In fact, I'm certain I haven't. So please turn to someone else on that one.
Oh, thanks, Kevin. So I'll offer to our panelists. Lindsay, you want to take on thoughts on research?
Yeah, so that is Glenn in Cleveland is a research center. So NASA does take a lot of value in research and development of these programs. I would say for space fission systems, we're not exactly starting from scratch. I mean, we have if you take it back to SNAP 10, 60 years of studies and designs that have been out there. And so I think where you're able to start identifying the knowns is when you are able to take those designs and start building and start actually piecing these systems together. And then that's when you'll be able to find out, okay, well, this is a gap area, and start identifying those unknowns. But to me, I get the sense from industry is they're ready to build, and you're going to learn a lot from the build of a system.
Thanks, Lindsay. Joe?
Yeah, I think the way I was looking at it, a little different tack maybe, is again, in terms of efficiency, part of what obviously we're trying to do with some of these standards is provide clarity so that, again, we can execute efficiently, understand what the requirements are that we need to demonstrate through research, through testing, that we are achieving, and have those agreed upon. I think as we've kicked off a lot of these newer projects, there's still a lot of uncertainty for the designers, for the customers, for the developers in what is either the total program cost, what's the total program schedule, what do I need to do to get to the end, and that uncertainty leads to risk and leads to budget increases, et cetera. So to be efficient, I think part of what the effort in these various working groups is to provide that clarity so that we can be more efficient in understanding if I do this, yes, then you've met your criteria, you can move on to the next phase.
Yeah. Thanks, Joe. Tina, your thoughts?
Yeah, if I can just add, I spent a lot of my career thinking about uncertainty and how to think about it ahead of time. And one of the things I would say is it's amazing how much uncertainty you get like a group of people who understand different parts of whatever system or problem you're looking at, it's amazing how much of the uncertainty you can actually kind of come up with ahead of time. I would say that you can really reduce the unknown unknowns by just having a systematic kind of way to try to think through all of the potential uncertainties. And then, of course, the next step is figuring out which ones are important. You know, they're not all going to be equally important. You want to be able to focus your research and your efforts on reducing the ones that actually contribute to the risk versus ones where there might be a lot of uncertainty, but it's kind of a no never mind in terms of the outcomes that you care about. So I think taking a systematic look with, again, group of people or groups of people who really understand all the different parts of the problem goes a really long way to, you know, just being able to focus, you know, resources on those things that matter.
Awesome. Thanks, Tina. All right, Lindsay, this is definitely a stumper question, so get ready. Is there consideration of using lunar or Mars terrain as shielding to both reduce the needed distance from habitats and the shielding requirements from the reactors? So building some space mountains for shielding.
Yes. In fact, one of our earlier fission concepts looked at burying the reactor into the lunar dirt, the regolith. That was the one about 2010. Regolith turns out to be an excellent shield of reactor material. There are a number of trades going on right now for are there efficiencies we can make on this shield? Even, you know, what we're doing a study on what would a realistic dose be on an astronaut, because they're going to have a suit on them and they're going to be in a habitat. How much time are they spending near the reactor versus not the reactor? And they will be a kilometer away right now. We had to kind of have a boundary condition for those early concepts so that they could build a system to still meet like a 5-rem at a kilometer away. But is that too conservative? We still want to make sure, you know, astronaut is safe, but let's take into consideration all these other things that they will have on them. Certainly, being able to bury a reactor in the regolith is ideal. It provide, I think it's like 7 meters of regolith between a person and the reactor is enough to keep them safe. So, but you have to look at it also as that could potentially be a single point of failure if you get up there and you're assuming you have a hole or a crater to put this into and it's not there, but you haven't adequately shielded the reactor. Now you're not going to be able to turn it on because you've got this potential issue. So there's always like a give and take, but it is currently being assessed is can we help, especially it all comes down to that mass, being able to get this up there. If we can figure out a way to have a pretty solid way to use that regolith, you know, can that shielding requirement come down for the design? But currently looking at that right now. It's a good question.
Thanks, Lindsay. All right, Joe, I got another stumper question for you. So this is from a commissioning engineer, so careful with the answer. They're looking for engineering detailed question or answer here. What unique components or system testing is necessary for space reactors?
So one of the challenges I know in terms of commissioning and bring these units, let's say, online is Tina mentioned uncertainties. So the data that exists, the nuclear data that's published out there, does not reach down to a lot of the temperatures that we need. So there's a lack of criticality data when you talk about -°C type temperatures or colder, you know, very, very low temperatures. So that starts to expand your uncertainties. Look at how are you, first of all, assembling it. You then add on thermal conductivity challenges, thermal expansion challenges from, you know, commissioning a system at ambient or room temperature, and then obviously having it go into an environment that is very different, vacuum, the radiation, background radiation from space in and of itself. there starts to add on a lot of challenges. One, in terms of what data is available, so that drives what experiments are going to be needed, and how do we achieve those experiments that are, again, trying to bring both the space environment and the nuclear irradiation environment together.
Awesome. Thanks, Joe. And Tina, question for you. Are there any insights from the DRACO program as it matures that are relevant to fully commercial efforts?
Yeah, thanks for the question. Yeah, the DRACO program, I think naturally, I believe, I don't know of any other missions. It may be the first one to demonstrate a nuclear thermal propulsion engine, which is, I mean, if it's going to be the first of the kind to do that, I imagine that there would be good insights that come out of that for future ventures who would like to do the same. So, I would say certainly can follow along with, the progress of that mission. There's plenty of information that is on their website. And maybe it's still a few years from actually launching, but I imagine, again, as a first-of-a-kind mission, that there will be a lot of good insights and lessons that can be used by future mission owners, planning to do the same.
Awesome. Thanks, Tina. Well, I am keeping an eye on the time, and we really only have time for one more question. I'm going to make it a softball. So, Kevin, you're up first. Favorite space movie? Hey, well, before you think very carefully, you're going to be judged. There's a lot of Star Trek versus Star Wars debates going on here in the room. So, favorite space movie, Kevin?
I'm going to take a totally different tact on this, and I'm going to say Spaceballs.
Excellent. Lindsay, favorite space movie?
Interstellar.
Interstellar.
Love that movie.
Oh, yeah.
Yeah, you stole mine, Interstellar.
Tina, your favorite space movie?
Oh, man, I was going to say Interstellar. So I guess we have a winner. What about you, Vic?
It's got to be Apollo 13. Forget my son. All right, on that note, I do want to thank, well, a lot of really good questions, so thank you. Again, catch us here after the session or email us. We'll try our best to get you answers. But really want to thank everyone online and here in person for making this a successful session and a successful RIC. And on that note, folks, it is lunch. Thank you.